Assalamu alaikum wa rahmatullah. Welcome to my class on distributed and parallel computing. To remind you, you will find all videos on my YouTube channel, so don't forget to subscribe and click the bell to receive all updates. Today, actually, we are going to discuss or to explain the something called processing elements architecture. So this processing elements architecture actually is under chapter 2, which is all about the parallel processing elements. If you remember, in the last class, we have taken some terminologies, which is the SISD, which means single instruction, single data, then SIMD, which is single instruction, multi-data, then multi-instruction, single data, and multi-instruction, multi-data. So this one, as we said, this is very serial, fully serial, and this one is semi-parallel, which is a single instruction, multi-data, and this one is a multi-instruction, single data. Actually, this two types of architectures are very rare and are not common. This one is very common, especially for computers with the single processor. In many houses, in many, personal computers, mobile devices, and so on. They are under this single entry or single instruction, single data, especially computers that has single processing element. Okay. For the MIMD is very common nowadays, especially in the latest decade or the recent decade. So all machines now become, or most of the machines become or includes multi-processors or multi-cores or whatever. So including some laptops, also some mobile devices, most of the servers, not most, all of the servers actually nowadays have multiple processing units. Okay. Current focus actually of this course is all about the MIMD model, which is very common nowadays, and which is the only architecture that can achieve real parallelism or real parallel computing. Here, this architecture actually is based on multi or distributed memories or multiple memories and also multiple processors. Okay, so let us go through quickly. Since I already explained this in the last class, I'm not going to explain in deep again. So in here in the SISD, we have only one data goes to a single processor at a time. So speed is limited by the rate at which computer can transfer information internally. Example, some PCs like Macintosh, Windows workstations, especially previous and old computers that has only a single processor. The second one here is the MISD, which is multi-instruction and single data. In this architecture, we explained in the last class that the same data will be passed to multiple processors and multiple instructions will be implemented or will be applied on the same data. So this kind of architecture can show some kind of parallelism, but it's not a fully parallel. Actually, it's something we can call it semi-parallel or whatever. There are many names about this. Actually, this one is not that important, especially for this course, because this architecture actually is not very common. It has only few examples already built in the real life. So more of an intellectual exercise than practical configuration. So this one is intellectual or means theoretical more than practical, but commercially not available. Okay, so you cannot buy a machine with this architecture. You cannot find it in the real market. Also, this one is SIMD architecture. This one also is not available in the market so far. Some examples, only the Cray machine vector processing or thinking machine. This one is the only example we have up to my knowledge, at least. I think this has been created or has been built in 1970 something, and now is not available in the market anymore. And Intel MMX multimedia support. So this thing can have multiple data given to multiple processors, but all processors will run or will apply the same instruction stream. Okay, this is actually not practical. That's why you cannot find it in the real life. The important one is the MIMD, which is the modern or latest architecture that's predominant now in the market of computers. So even personal computers and even mobile devices now has this architecture, because they have they could have multiple instructions and multiple data at the same time due to having multiple processors, and each processor could have its own cache memory or whatever. And also in the big architectures or big computers like cloud computing environment or grid computing environment, that environments also are based on the what they call it MIMD. So here, unlike SISD, MISD, MIMD, computers works synchronously. Sorry, this one here. Unlike SISD and MISD, MIMD computer works asynchronously. Asynchronously means each processor can work independently. So they don't have to do synchronization between all or among all processors, because every processor could run some different instructions which is maybe related to the same application or maybe related to different applications. That's why this architecture can work synchronously and asynchronously, both of them. But for the previous architectures, all of them have to be synchronized. All of them have to be synchronized because they are sharing some things. Maybe they share the same instruction or maybe they share the same data. But here for the MIMD, they only share maybe the same machine or whatever, but the processing will happen independently because the instruction is different, the data is also different. So no point to make it synchronized unless we have a purpose for that. So here in the MIMD, we could have what they call it shared memory MIMD, which is called tightly coupled, and also we could have distributed memory MIMD, which is loosely coupled. Okay, then here we start with shared memory MIMD machine. Okay, shared memory MIMD machine actually has multi-processors, because this one is, don't forget, it's an MIMD. That means it has multi-processors. But those multi-processors have only one global memory system, and that memory is shared. And all of that processors will be connected to the memory through the memory bus. Okay, so here each processor could implement or could run different instructions than the other processors, and also using different data from the same memory. They can use different data from the same memory, and also they can share the same data. So both of the scenarios are possible. Okay. because this architecture is very wide, then it can implement all of the scenario, all of the previous scenarios. Okay. Communication here, source, this one PE means processing element. So source processing element writes data to global memory and destination retrieves it. So maybe there are some application that have multiple tasks. So every task is running in different thread, and maybe the task, the first task is using the processor A, then that task will do some processing on certain data, then after that it will save something called X in the shared memory, then after that maybe processor C will need that X, or maybe processor B need that X to solve other issues or to perform other tasks. Okay, and also they can save their own data in the memory that's related to the instruction run on that processor. Okay, so they can use the memory to communicate. So that's why here we see communication. That means they can use this memory or shared memory like whiteboard. So somebody write and maybe others can read. Okay, easy to build conventional operating systems of SISD can be easily ported. Okay, so yes.
So the multiple processor, is it is it multiple processor or multiple core? It means like you have many core.
Actually, multi-processing machines could have real multiple processors, and could have only a one physical processor that has multiple cores inside, multiple physical cores. And some of the processors are only one physical processor that have multiple virtual cores. Multiple virtual cores.
Oh,
Yeah,
okay.
that looks to work in parallel, but in reality, it's actually what they call it multi-threading processor, which divided the time into small slices or slots. Then it can shortly run certain task, then quickly switch to other tasks to show you that, or to be acting like parallel processor. Okay, so the real architecture is not that big issue. So if we can see here, what they call it, multi-physical, I don't know whether we can see some pictures or not, multi-physical processor computer. I hope that we can find some pictures to show you. I have one, actually. I have one server in my research room that has 4 physical processors, and each processor have 10 cores. So in total, we have 40 cores. And that machine has 128 gigabyte RAM. Yeah, I have it in my room, actually. If you are interested, you can come to me after they open. You can come and see the machine. So this is a motherboard that could have multi processors. So this is a physical processor, and this is another physical processor. Okay, so this physical processor could be i7, could be i5, could be i3, could be Xeon, could be whatever, depends on the model of the motherboard. So if, let's say, Xeon, so maybe that Xeon processor can have like 10 cores, or maybe 16 cores, or whatever. So in total, in that case, it could be 20 cores, or 32, or 40, or whatever. And inside this processor, actually, it's called parallel processing element. Why? Because it has multiple physical cores. Multiple physical cores. This, you see, this motherboard can fit for 4 processors, 4 physical processors. Okay. Now let us see multi-physical cores processor. Yes. Like this. Inside the same processor, I would try to find for you a real picture maybe, or something that's more clear. Yeah, I think this one is very clear, this one, because this one here is a processor. This piece actually is a processor, and this one is a quad core. So I don't know, maybe this one has 2 cores inside. I'm not sure how they, or maybe we can see this one. This is 1 core, 2nd core, 3rd core, and 4th core. Okay, and this is the shared L3 cache, which is also available inside the processor, which is called L3 cache memory, and other components. Then here they have something called memory controller to communicate to the shared memory, and which is the RAM, and to exchange data between the memory and the processor. Okay, so we based on this, let me print draw something on the screen to explain for you. So based on this here, based on this architecture, we could have one PC. This one is PC, right? So that PC could have one processor, and inside that processor, I will write B here, P, okay, for processor. Then inside the processor here, we could have only single core. Some processors are single core, right? Like Celeron. Celeron is only 1 core actually. It doesn't have multi-cores. Okay, so this is one of the scenarios. But what if we have what they call it multi-core processor, like dual core or core to do, which is very old. I think dual core and core to do already out of I mean the market. So in the case of dual core and core to do, we have 2 cores, 2 physical cores inside the processor. And also, if let's say i3 depends on the model, depends on the generation actually, and the class of the processor, because this field actually is very complicated, because for example, some of the i7 processors, you can see they have like 4 cores. Some of i7 they have 8 cores. Depends on the model, the generation, and the class, many other things. So this is what they call it multi-core processor. Now this one called quad core. There are some processors called octa-core. Octa-core means have 8 cores, and so on. Okay. Then later, inside the same machine, we could have this processor only with multi cores, and also we could have real physical processors that have multi cores. So maybe 2, which is called dual processor, or maybe 4, which is called quad processor. So in this case, if let's say we have quad physical processors, and every physical processor has 4 cores, then in total this machine will have 16 cores. And each core could run like a single instruction with single data, or single instruction with multi-data. So this processing unit will act like one what they call it serial or sequential computer. Okay, so in this case we could run concurrently 16 applications at the same time, really at the same slice of time. We can run independent 16 tasks. Okay, is that clear?
Yes.
Yeah. I will show you more things actually to let you know. In each machine, most of you I think using Windows. So if you use Windows, you can show this task manager. So to show the task manager, you can press the Control Alt Delete. Then it will show you the blue screen. Then from the blue screen, you can find the task manager, or maybe you run like that. You can write task manager like this, and it will show that here. So for this, if you open this, you can see how many tasks you have running at this moment. But these tasks actually are not all of them running at the same time. Why? Because in this machine, we have multiple CPUs, but that multiple CPUs or multiple cores cannot fit for the big number of tasks that we have in the memory now. Now, as you can see, we have 138. So that's why we have a scheduler to control the tasks and switch between them. Okay, so here we can see the performance. If we go to performance, we can see the CPU here. You can see we have 2 cores and we have logical processors 4. Logical processors, we have 4. Okay, and also this machine has 2 GPU 0 and GPU 1. So this also can do kind of processing, depends on the applications that we use. Okay, actually why this GPU is very busy, because actually I'm recording now. I'm using what they call it OBS, this one, OBS Studio. As you can see, it uses the GPU 0 to record. Okay, because this one is all about creating video, right? So that video is a kind of graphic. That's why they use the GPU to make it more faster. Other things here, like this, you can see Cisco Webex is using the CPU here, but we don't know what CPU is that. So if you want to see details, you can, I don't know whether we can show some details here or not. Because this one actually is very basic. So if you want to, if you are interested about the very deep details, you can find some of the free tools available in the Microsoft market or online. In many websites, they provide this kind of tools. As you can see here, in general, this machine actually it's an i7, which is the 6th generation, and this 6000 means 6th generation, and U here means a class, the class of the processor. Okay, so they have many classes actually. If you go to Intel itself, under the i7 only, for example, the 6th generation or 10th generation or whatever, you will find too many classes of the processors. So for example, U maybe AX or UX or whatever. So everyone has its own properties, number of processors, and number of cores, and whatever. Okay, so if you are really interested about that, you can go and deeply search inside the Intel, for example, i7 processor 10th generation classes. Okay, we can go here. Hopefully it's the thing that I'm looking for. Oops, this shows some computers. Okay, let us go to, can you see Intel Core? Okay, let us take Intel Core and see Intel Core X series, Intel Core i9, i7, and so on. Let us take, for example, i7. Okay, i7 here, if you can see, we have F series, we have T, we have KF, we have K, H, G7, 7E, GRE, G7, and so on. So here, if you can see, this one, F, has 8 cores. Maximum turbo frequency is 4.9 and processor base frequency is 2.5 and cache is also 16 and so on. Okay, let us try to find U. Is there U here? No, I don't think, right? There is no U. This one, 11 generation. Is there all generations here?
No.
No. Okay. Yeah, anyway, if let's say, let us take this, H. The first one is F, right? This one is H or K. K is also has also 8 cores, and here the frequency is 5 gigahertz, and also the processor base frequency is 3.6. That's why you can see the price is much expensive, more expensive than that. This one also is more expensive. I don't know what's the difference between this and that, but as you can see, it looks the same, but the price is very different. You see, it's about 60 US dollar difference. So if you go in deep and read about them, you will find the difference. Okay. This one, for H, for example, it has only 4 cores, and the frequency is 5. The cache memory is 12 only. This one is 16. Actually, the cache memory is crucial, is a very important thing. Actually, if you are looking for a very fast machine, you have to consider this. You have to know about what cache you have in your processor. The more you have, the better you perform. Okay, so if you see this one, G7E or GRE or this kind of types of the same i7 Intel Core, you will see that this one is only 4 cores and the frequency is 440, and here the base frequency is 1.8, which will give you a very slower performance compared to this. Okay, so the thing is very complicated. Actually, it cannot be covered in 1 or 2 slides, or even in 1 or 2 classes. Cannot be covered. This one is very detailed and also is vendor related. So if you see the Intel, you will have many types of processors under Intel. As we can see here, we have many families, right? I don't know where they go. Yes, processors. Here we can see many families of processors. Xeon scalable, Xeon processor, Core processors, Pentium processors, Celeron, Atom, Movidius, Vision, and also processors for IoT. So you see 1, 2, 3, 4, 5, 6, 7, 8. 8 families. Then inside each family, if let's say we talk cores, we will see 1, 2, 3, 4, 5. 5 families. Inside each family, for example, the i7, as you can see, if you remember, we just now opened, we have like maybe 10 or 15 types of i7, right? And also this is for a certain generation, for example 10th or 11th or 9th or whatever, because we have many generations, right? So every generation has its own characteristics and properties. So if you also go to Core, for example, you see how many we have. Xeon, we have 3 families of Xeon: E, W, and D. If you go to E, you will find many types of processors also. or maybe only one or whatever. I don't know. You see list of Xen processors, very much, right? We have 8 cores, we have 4 cores, 6 cores. Yeah, and what if we go back and we take this again and we see the W. You see in the W family we have 10 cores. This is the one that I have in my machine. And also we have 18. We could have 18. We could have 12, 14, 24, 28. Many types, many different numbers of cores. Depends on what model exactly we have. Okay? Also, if you go to, for example, AMD processors, you will have also a very big list of processors. They have Athlon, Opteron, Zen, AMD Phenom, Sempron, Zen 2, blah blah blah. Many types of processors. So I am not sure whether to find this here or not. The latest AMD processor is what they call it Ryzen 9. Ryzen 9 actually is very fast, and it works very fine for graphics, for games, for many other things. So here, if you can see, let us take the AMD Ryzen 9. Let us see its specifications if we can find. So it has 16 cores, guys. It has 16 cores, and it's up to 4.9. So its performance is similar to the i7. Okay. Its L3 cache is 64 megabyte. The base frequency is 3.4. It's actually is very fast. And this is the power. Actually, you have to consider this if you are interested about the what they call it power consumption. Okay, you can go through and you can understand about this brand or this model of processor, and you can compare it with other processors. This is if you want to go to certain companies' websites. For example, AMD, it will show you AMD processors. If you go to Intel, it will show you only the Intel processors. But if you go to third-party websites that's related to or interested in all types of processors, then you can find some tools to compare between different brands of processors. For example, Intel and AMD, you can select multiple processors from different vendors and you can compare them easily. So maybe we try to compare AMD, what they call it, Ryzen and Intel i7. We see if we can find them. So like this, PC World. I think most of you knows what is the PC World. This is what they call it, PC Magazine. Actually, this is very famous magazine that that's established, I think, in the early 19s or maybe even 80s. It's all about computers, and it has a lot of benchmarking, a lot of ranking for example, for computers, for processors, for RAMs, for softwares, for antiviruses, for operating systems, everything related to computer. So it's really interesting, and they have some tools actually here, but I'm not sure where to find. I remember that time I saw they have a tool that allows you to select what type of processors you want, then easily it shows you the comparison side by side. Okay, yeah, like that. Okay, you can see here the architecture, the socket type, the cores. This one has 8 over 8, this one 8 over 16, 3.6, 3.7, and this is Core i7, and this is Ryzen 7, not Ryzen 8. sorry, not Ryzen 9. And as you can see here, the boost frequency from here and here, and also the L3 cache, process, TDP, memory speed, memory controller, integrated UHD graphics, like that. This one, no iGPU. And the price is like this. So as you can see, the price is much cheaper and the performance is quite interesting. You can find many tools actually to show you the comparison between processors. Anyway, guys, this is actually out of the scope of our class, but I wanted to link your thoughts to the real market and also to the real components that we have in the market. Also, in this task manager, you have something called Open Resource Monitor. If you want to, if you are interested to see more details, you can open that, and that will show you more. More details for the system, for the resources. So, for example, if you open the CPU here, you can see more details here, and you can see the performance of the CPU. Also, you can go to the CPU tab here, and you can see CPU in total. This one surface CPU users, this one CPU 0, 1, 2, 3. So that means we have 4 cores here in the system. Okay. Also, you have the memory, you have the disk, the network, and so on. Okay, this is very interesting tools and very important actually to know how to use them, especially when you do some kind of software development while you compiling your software, so maybe running some queries on your SQL server or whatever. You need always to do some kind of optimization to make sure that your products are very good and can run on the optimal level. Okay, so that's all about the multi-processor and shared memory. Okay, easy to build here, conventional operating systems of SISD. So if every processor could work on this mode, SISD, and also it can work for as SIMD. Okay, limitation of this. Actually, reliability and extendability is very limited for this kind of machines. Memory component or any processor failure affects the whole system. So if, let's say, you have multi-processors here in your laptop, multi-cores processor in your laptop, and for example, one core has failed or maybe stopped working. I don't know which whether this scenario is real, can happen or not. I never seen a processor that has one core inside that cannot work. I never seen that case. But if, let's say, one core stop working, then you cannot extend, right? Unless what you can do is only to replace that damaged part, which is the entire processor, throw it and bring another processor to return your operating system. Your machine. Also, you cannot increase the number of processors. If, let's say, your motherboard supports only one processor, you cannot extend unless you change the entire thing. Okay, this is what they call it, extendability. And reliability actually you cannot rely on, because if a failure happens, then the entire system will stop. Okay, because everything actually is based on a single machine. We still based on a single machine. A memory component or any processor failure affects the whole system. So increase of processors lead to memory contention, because we have here multiple processors, and all of that processors could exchange data at the same time to the shared memory. Then here at the shared memory, we will have a kind of bottleneck. Okay. Example of this kind of machines is what they call it, silicon graphics supercomputers. Okay. Then here we have distributed memory, MIMD. So MIMD means multiple processors, but here we have distributed memory. So each processor has its own memory. Okay. Here communication. This one IBC is called the interprocessor communications. Means the communication between the processors. IBC on high-speed networks. So here the communication between that processors is, as you can see, they have kind of very fast of high-speed channels between the processors to increase the speed of entire system processing. Network can be configured to tree, mesh, cube, etc. So this one actually, the network that connects, I mean the IBC network could be formed in multiple shapes like tree style or mesh style or cube or ring or whatever. Okay, unlike shared MIMD, this easily readily expandable, so we can expand expand the number of processors, also the memories and so on. This one highly reliable because if a failure happen in one processing unit or in one processing element, the other processing elements will continue functioning. So any CPU failure does not affect the whole system. Okay, let us go here to laws of caution. This is very important thing actually, especially when we talk about designing or having or buying multi-processing computer or multi-processor computer or multi-core computer to have or to build a kind of server to provide some services to maybe customers or students in the university or whatever. So we have to consider all of that concepts. One of them is the laws of caution. So here, the speed of computers actually is proportional to the square of their cost. So as you can see here, cost equals the square root of speed. And also the speed is equal to the cost square. So here, if the speed increase, the cost will increase for sure. If the speed increase, the cost will increase, right? So as you can see here, the relation is linear. And also whenever the speed increase a little bit, the cost will increase much. Also, we have another concept of speed up by a parallel computer increases as the logarithm of the number of processors. So here, speed up equals to log 2 of the number of processors. So here, as you can see, the x-axis is the number of processors, and the speed here is the y-axis. So if let's say we increase here from 1 processor to 2, we can see that the speed increases very fast here. From 1 to 2, there are a very big difference. But from 2 and 3 or 4, the difference will start become smaller and smaller until it will become steady. Then we will reach a certain point. After that point, even if we increase number of processors, the speed will remain the same. Okay, so this is the logarithmic relation between the speed up and the number of processors. Any question about this?
No.
Actually, this course is not deep detailed. And also the level of the course actually is not very advanced. It's only an introduction, I think, of the distributed and parallel computing. That's why we don't have that kind of calculation, that kind of very complicated problems or very complicated problems that require mathematics or very complicated solutions. We don't have that. The only things that we have is very simple relations like that. So maybe even in the exam, maybe we can find one question, for example, asking about the cost, the relation about the cost between the cost and speed. And for example, we give you a scenario, then we ask you to calculate the cost or the speed or whatever. Very simple. Yeah. Here, caution. Very fast development in parallel processing and related area have blurred concept boundaries, causing lot of terminological confusion. So because of this, because of parallel processing, there are many confusing terms actually, like concurrent computing, concurrent programming, parallel computing, parallel processing, multi-processing, multi-cores, distributed computing, multi-threads, many things, right? Many terminologies that makes it confusing, right? Do you know what is the difference between concurrent computing and parallel computing?
Is it serial and sequential? Is like
No. That one is
okay.
sequential. Concurrent and parallel actually is the same thing. Parallel computing means we concurrently run multiple tasks at the same time. Concurrently means at the same time. Also, simultaneously. Simultaneously means at the same time. Concurrently is at the same time. Parallel is at the same time. But multiprocessing is a little bit different, because multiprocessing is talking about the architecture itself. So maybe we have a multiprocessing machine, but we run only a single process on it. Or maybe we have multiprocessing machine and we have a sequential operating system. So everything will be run in sequential mode. But concurrent computing or parallel computing means we have multi-processing machine with multi-processing operating system that could run multiple tasks at the same time. So from here, the first and second point actually talks about the entire system, including hardware and software, that's ready to run real parallel or concurrent tasks. But this one is talking about somehow actually you cannot 100% say that, but in some way this talks about only the architecture. So if let's say the software does not support that architecture, or maybe supports some parts of that architecture, then we will not successfully be able to run multi parallel tasks at the same time. Okay, then what we have something called distributed computing. Distributed computing actually is a different type of architecture. Distributed computing can run a single process on multiple units that's geographically and physically located in different places. So it could run one single task on multiple units that's physically located in different places. And also it can run multiple tasks on that physically distributed units. So each unit can run one task. So this distributed computing is a kind of concurrent computing or parallel computing, which is also multiprocessing, because each physical unit that's located in different place physically, it will have its own processor and RAM, and also its processor could be single processor, could be multiprocessors, could be multi-cores, could be a hybrid like multi-cores with multiprocessors. You understand what I mean?
Yes, sir.
Yeah, distributed computing is like cloud. In the cloud, actually, we have a very big data center that has a huge number of computers or a huge number of servers that are connected to each other in one controller or to one controller to appear to users as one unit. So all of that computers will be connected to one controller, and we as users, we can see it as one computer. We don't know on what server we run. And even sometimes we don't know on what server that's located in what country we run. We don't know. So for example, if you upload one file on the Google Drive, you don't know where your file is going to be saved, right or no? You don't
Correct.
know whether it's saved here in the Asian Google data center, or maybe on the European Google data center, or maybe it can have multiple replicas of the same file. Maybe one replica here is local in Singapore, maybe the other replica is in Europe. We don't know. Nobody knows, right? Then when you upload your file to the Google Drive, for example, which is a part of the cloud, your file actually is going to be processed. When we send, for example, I upload my file to the Google Drive, and you upload your file to the Google Drive. We upload to the same website, right? To the same address, right? Right or not,
Correct.
guys? Yeah, we upload
Correct.
to the same address. In our browser, we have the same address. The only difference is the ID number of the user, right? My ID is different than your ID. But both of them supposed to be on the same server. But maybe your file is going to be, for example, processed by server number 120, and mine is going to process on server number 452. Nobody knows which server is going to serve you, which real physical server is going to serve you. The only thing we know is that the Google Cloud is going to serve us, right? Okay. In general, how the cloud works, actually the cloud is like this. The cloud is like this. Let me make it very clear. So I will try to shorten the thing. Okay. Suppose that this one actually is a computer or server instead of this PC, because the server is also kind of computer, right? Very advanced computer server. Okay. This computer actually, or server, I will try to make it smaller, resize, then we try to make it 25%. Okay, like that. Then this computer actually is going to be like this, like that. So it could have multi-processors, multi-cores, whatever they have in each machine, like that. Then until n of the servers, right? So let us put some kind of dots here. So dot, dot, dot. Oops. The paint is very painful actually to draw it. Anyway, this is means server 1, server 2, server 3, server 4, and server n. We don't know the n is how much. Maybe 100 servers, 1,000 servers, 10,000 servers, we don't know. And for your information, in the cloud, normally they deal with thousands of servers in the same data center. I don't want to say tens of thousands. I don't want to say that, but this is real. Okay. And also we have multiple users, right? These circles, I will put them as users. So that users could be located in different countries, different continents, different places, right? and all of them are going to communicate with this system through the cloud, right? Through the cloud, like this. Oops. See? So each user is going to communicate through the cloud to access, for example, the Google Drive. And they are going to use the same address, right? As I mentioned. Okay, the same address cannot be, assigned to this huge number of servers, like 10,000 servers or 20,000 servers. We cannot assign the same IP address to the same, to this number of machines, right? Okay, so what? How we can make it? That's why they have something called controller. I don't want to go and use very complicated names, but simply I will make it controller. Controller. Okay, that controller is the interface between all of that users and those machines. So all of them, they are going to communicate to through the same controller, and that controller will distribute the tasks. So maybe user X is going to be served by server 1, maybe user Y is going to be served by server 2 or whatever. And actually, this is not the true scenario. This is not the true scenario because each server can handle very huge number of users. Because here, this server may have like 64 processors or maybe 64 cores, and each core could handle one user or maybe even multiple users. So that's why we can see like 10 or 15 or 100 users handled by server number 1, then the coming 100 or 200 users is going to be handled by the second server, and so on. And it could be also distributed in different manner. So maybe some kind of this controller maybe distribute the tasks through the servers, depends on the type of the service, or maybe depends on the type of the file. So if, let's say, maybe files are pictures, they save them on what they call it, disk store number 1 or 2 or 3 or whatever. If, let's say, they are documents, they save them in different place through a certain server. We don't know how they control or how they construct their system and how they distribute the tasks, because this is their secret. But what the important thing we need to know is that the operating system that could handle this controller is able to distribute the tasks in each manner, in every manner. So if you want to distribute the tasks, depends on the location is okay, depends on the type of the task is okay, depends on the file type is okay. You can do a lot of things. Okay. Okay, guys, is there any question?
Okay, doctor.
Actually, the scenario is not as simple as this. I mean, the architecture, but I wanted to simplify. I just wanted to simplify for you. One more thing, guys. In this case here, in this case, what we have to have actually is an operating system, right? So the operating system actually will be running here on the controller, and also each server should have what they call it, an operating system, right? And this operating system should be configured to be controlled by the controller, like that. So that's why we have multiple types of operating system running on the cloud here. And later we are going to see what types of operating systems we could have. Okay? Any question, guys?
So far, no, doctor.
No, doctor.
As I said, guys, this class is theoretical. Please don't get bored, because too much theory is sometimes making you bored. But this thing is very important. This class is very important. Why? Because it opens your eyes on things that you never seen. So if you keep using the cloud tasks or the cloud services blindly like that, so maybe other people will make fun of you. If they know that you don't know about the architecture of that cloud or how it works even in general. Because you will graduate as a computer scientist, right? So you suppose at least to have an idea how that thing work, how this thing work, what kind of main components they have in the cloud, for example, or in a distributed system, or what kind of options we have to select among them. So maybe after you graduate, you go to a company that, for example, asks you to make a proposal for them to install what they call it private cloud, maybe in their office or in the maybe the main branch of the company or whatever. Then it's very bad if you say I don't know. It's really bad. Yeah, you can say I don't know much details. You can say that, but you cannot say I don't know anything about it. At least you have an idea. You know that we have a kind of cloud computing, we have grid computing, we have parallel computing, we have sequential computing, we have all of that types, at least. Yeah. Okay. Okay.
Yeah, okay.
Now we came to operating systems for high performance computing. So I already explained to you some introduction to the operating system that's related to this environment. So here, types of parallel systems. Actually this slide supposed to belongs to the previous part, but anyway, they repeat the same thing that we have already explained. So the first type of parallel system is what they call it shared memory parallel. So in this case, we have one memory and multiple CPUs, and all CPUs share the same memory like whiteboard. So one can write, others can read. Okay. This one has a smallest extension to existing systems. Program conversion is incremental. Distributed memory parallel. So in this case, each CPU has its own memory. Then they use a network, very fast network, to communicate among those CPUs. So completely new systems. Programs must be reconstructed. Then we have clusters. Clusters actually is a very huge system, or a very huge parallel system that includes a number of computers, number of standalone computers. Okay, that computers could be desktops, could be servers, could be laptops, could be mobile devices, could be whatever. But the only important thing is that they have to be connected to each other through a very fast network, and they should have at least one unit to control them. At least one unit, one computer to control them. So that computer will work as a scheduler. So the tasks will come to that main computer, then that computer will decide to what subcomputer it will be sent. And that subcomputer should be responsible to process that task. Then after the task finished, the result will be returned back to the controller. Then the controller will give it back to the user. Okay, is that clear, guys?
Yeah.
Yeah.
Yes, doctor.
This thing actually is highly extendable, highly scalable. So at any point of time, we can increase the number of computers, then the capacity of our cluster will increase. So for example, if let's say we have like 10 computers, we connect them together using very fast network, then we configure one of them to be controller. Then after that, we can handle like, if let's say 10 computers, maybe we can handle 10 tasks at the same time if we suppose that subcomputers are single processor based. So in that case, we can handle 10 tasks. What if we want to handle 20 tasks? Easily we can bring extra 10 computers, we connect them together to the same controller, then we will be able to handle 20 tasks at the same time. Okay, the sweet thing in clusters actually is that we can use or we can utilize the old machines that we have. So for example, if let's say in the Faculty of Computer Science, if let's say in our labs we have like 200 computers, then one day those computers, the management decide to change them. So if the faculty wants to sell them, they will get nothing, right? They will sell them very cheap. So maybe like 20 ringgit or 30 ringgit per PC. So instead of selling them very cheaply, they can take them, put them in a certain place, communicate them using a very fast network, then they can utilize them as a server. And that server could serve many applications in the campus. Okay? You got the idea, guys?
Yes.
Yes.
Yes, doctor.
Okay, but the main point here is what kind of operating system that could run that tasks or could fit that cluster. Because here this cluster will be seen by others as one computer, as one server. So others cannot communicate directly to subcomputers here in the cluster. They have to go through the same controller. They send the tasks or their requests to that machine. Then that machine will handle the tasks through the subsystems. So for example, suppose that they use 4 machines and one controller to serve as web server, So maybe the university, maybe UBM, makes one PC to serve Putra Plus, and other PC to serve SMB, and other PC to serve, for example, the SGS website, and maybe other machine to serve like the main website of the university and all faculties, for example. Okay, so this is how they can, separate or split the entire system into subsystems, and each machine will be responsible for a certain task. So if requests come from students or from staff through that controller, so maybe one staff wants to go to the IGMS of the SGS, the controller will send the request to this machine. If let's say a student wants to go to the Putra Blast to see his PowerPoint slides or whatever, the controller will send the request here to this machine, and so on. So what kind of operating system can do that? Is it Windows, for example, Windows 7 or Windows 10 or Windows Server or whatever? Yeah, this is a big question, okay? Here, before we continue, I will tell you that there is some operating systems that can be used for clusters. Certainly can be used for clusters. And some other operating systems cannot be used for clusters. It can be used only for single or parallel machines. One single or parallel machine. Like Windows, like many types of Linux. Yeah. Also many types of, or many versions of Mac OS, and maybe Unix, maybe VMware, maybe whatever. We have many types of operating systems, depends on the vendors, depends on the architecture, and many things we have to understand, actually. That's why we came to this slide. Okay, operating systems for parallel processing. One of the parallel processing operating system that's well known is called massively parallel processing, which is MPP. MPP. This is actually reflecting the architecture of the system. So MBB systems having thousands of processors requires operating system radically different from current ones that we know. Okay, so one of the types of massive parallel processing is the cloud. Cloud is considered massively parallel processing. Also the grid, yeah, because they could have thousands of processors, maybe thousands of memories, maybe thousands of disks also. That's why they require a special operating system that could handle all of that stuff at once. Okay, so every CPU needs operating system, right? So every CPU need to be controlled by an operating system to manage its resources, to hide its details, and so on. So traditional systems are heavily complex and not suitable for MBB. Traditional operating systems actually like the systems we know, like Windows 7, Windows 10, Linux, Ubuntu, whatever like that. What they call it, the normal or personal operating system, or operating system for personal use. Here in this slide, framework that unifies features, services, and tasks performed. So that operating system, the operating system we need for the MBB actually should be able to unify features, services, and tasks should be unified. Three approaches to building operating systems. We have three main types of operating systems here. We have one called monolithic operating system, and we have layered operating system, and we have microkernel based operating system. So this microkernel is could be client server, or could be suitable for massive parallel processing systems. Okay, so here simplicity, flexibility, and high performance are crucial for the operating system. So that's why operating system, which is called microkernel based operating system, that's suitable for the cloud computing and the parallel computing, they are very, they have very high level of simplicity, very high level of flexibility, and also they highly perform their processing. Okay. Okay, let us go to the monolithic operating system. Monolithic operating system actually is the operating system that's very tightly connected or linked to the hardware. So similar to, for example, Windows or the personal operating systems. So here we have hardware, we have some functions, then the system services that could be provided to the applications. Then the user could use the applications directly to have some services. So the kernel mode is starting from here, including all of that stuff. Okay, including the service, system services, functions, and the interface to the hardware. So better application performance. This one could provide better application performance. So applications could be performed very fast, because as you know, when we talk about personal computer, actually is private. You can use it alone. So nobody is sharing your resources, and your resources are very near to you. So you don't need to use internet to communicate to the resources as when we deal with the cloud. So that's why the applications could perform very fast. Okay. But this thing actually is very difficult to extend. You cannot extend the capacity of your computer easily. Okay? We have something called layered operating system. So layered operating system actually, they have they divide the kernel into multiple layers. So the first layer is the hardware, the second layer is a process schedule, The third layer is the memory and I/O device management, and also another layer called system services. Then after that, we come to the user space, and we can see how the applications can communicate with the system through the operating system. Okay, this one easier to enhance. So if, let's say, we have an issue in the surface, in the system services, we can do some updates for the system services only. Maybe we need to upgrade, for example, or update some algorithm or whatever. Then extendability or enhancement is very easy. Okay, each layer of code access lower level interface. So they have the communication is very clear actually between layers. And they have some kind of hierarchy here. Also low application performance. So in this case, the application performance is a little bit low compared to the previous one, because this one should go through many stages or many layers, and between each layer and the other layers, we have to do some kind of what they call it encapsulation or decapsulation, which requires extra processing overhead. Okay, is that clear, guys? In general, is it clear or not?
Yes.
Okay. Traditional operating system here, I don't know what's the meaning of traditional operating system. Traditional could be personal, could be server, client server operating system, could be whatever. There are many traditional operating systems. I don't know how to really explain this. But I think we already covered all types of traditional operating systems. So here we have new trend in operating system design. Here we have servers and we have microkernels. So servers actually at the user space, and the kernel space includes the microkernel, which is very close to the hardware. And okay, let us go through, then I explain to you in general what's the meaning of that. Microkernel client server operating system for MBB systems. So as you can see here in this slide, we have many things like in the user space, we have display server, we have network server, we have file server, thread library, we have client application, and many other components, right? Here we have this type of line for send, this type of line for reply. So if, let's say, a client application requests some services, they have to go through the microkernel operating system to communicate to the other components. Then after that, that components could reply through the hardware or through the microcontroller, the microkernel, to the requesting client. So here, tiny OS kernel providing basic primitive process memory IPC. IPC, as I mentioned before, it means inter-process communication or inter-processor communication. So traditional services become subsystems. Okay. So here, when we talk about something called microkernel operating system, we will have that microkernel operating system, and also we will have a traditional operating system that will become treated as subsystems. So here we have microkernel operating system, and here maybe we have file server. This file server may be running Linux, or maybe running Windows Server, or maybe Windows 10 or Windows 7 or whatever, to provide the file service or to work as a file service provider. Okay, and also we could have a database server, for example, that's running on, for example, Windows or Linux, to provide database services through the microkernel operating system. Okay, So the microkernel operating system actually is going to be installed on the controller. It's going to be installed on the controller. Then the other servers could run different traditional operating systems like Linux, Windows server, whatever they can run. Then after that, we have they have to be configured along with the microcontroller to provide certain services to users. Okay, so in general, in this case, the operating system of the MBB actually is a combination between microkernel and traditional operating system of the subsystems. So maybe if, let's say, we have one server running Oracle database using one of Linux servers and another server running, for example, Microsoft SQL database using Windows server, and here maybe we have FTP server using, for example, VMware or maybe Linux or Unix or whatever, and maybe other type of servers. Then all of that servers use their own operating system, and they are somehow configured to communicate to the microkernel operating system to provide certain services to the clients. So clients does not know about what type of operating system is running on the server. So that's why the microkernel is going to hide a lot of details. It will hide a lot of complexity also. Maybe that FTP server actually is a complete cluster that has like 200 PCs. So that server actually will have a controller, and that controller will deal with multiple machines to save files, save or retrieve files. So also in that case, that cluster is going to be, the details of that clusters are going to be hidden by the microkernel. Okay, guys, is that clear?
Yes.
Yeah, doctor.
Okay, examples of microkernel operating systems is Mach, this one, very famous. Then Paras, Chorus, many people pronounce it in different ways, and etc. There are other very few examples of microkernel operating systems. Let us go here and see what is the difference between monolithic operating system and a microkernel operating system. In the monolithic operating system, as you can see here at the left side, we have this actually between this line here and that line. This is what they call it, kernel mode or kernel space. Kernel mode or kernel space. So as you can see here, everything between the application, which is in the user space, anything between the application and the hardware actually is called kernel. So the operating system will include all of that parts here. Okay, so all of them will be running on the same machine, all of this stuff, 1, 2, 3, 4, they have to be physically in the same machine, located or running over the same hardware. Okay, but this kind of operating system, which is microkernel, as you can see here, we have basic IPC, virtual memory, and scheduling only. So only this part, about this part only, and some of this part. But other services like file system is located on different server. So here the microkernel operating system is running only the basic services that could run the needed services on different machines. Okay, so this machine will have a traditional operating system, maybe traditional, maybe also microkernel or macrokernel or whatever, that operating system could be layered, could be hybrid, could be many types, actually, many architectures. And also here we have device drivers, we have Unix servers, we have application IBC, many things, many servers could run behind that microkernel. Okay? Then here, in this slide, we have something called, actually I modified this just now before our class, because when I go through the slides, I found some mistakes that need to be modified, actually, because in the previous slide, they mentioned that Windows is microkernel. Microsoft Windows, they mentioned that it's a microkernel. And in reality, Microsoft Windows is a hybrid kernel, and you can see this link. The reference is here. They said Windows actually is macro kernel, not microkernel. Macrokernel means hybrid. Okay, so here microkernel, as I explained in the previous slide, there are Mach, CMU, Paras, CDAC, Chorus, QNX, yeah, and others. For macro kernels, we have Microsoft Windows, which is totally hybrid kernel. So as you can see here, this is the hardware here, and this is the interface between the hardware and the operating system, which is called the hardware abstraction layer. And after that, we have the microkernel. Okay, this one, microkernel. And also another kernel, which is kernel mode drivers. So here we have two kernels. This one is micro, and this one may be layered, or I don't know exactly what structure or architecture they use here for this kernel. That's why they call it kernel and hybrid, and they make it or call it macro kernel, not micro. Okay. Then after that, we have the execution. Inside the execution, we have the I/O, we have the security, we have the IBC, virtual memory, process manager, and many other things. Then after that, we go to the user space, and we can see in the user space we could have the applications and so on. Okay. Then here again we go back to the single instruction, single data, which is a serial non-parallel computer. Single instruction, only one instruction stream is being acted on by the CPU during any one clock cycle. Single data, only one data stream is being used as input during any one clock cycle. This is called deterministic execution. This is the oldest and until recently the most common form of computers. This is the most common form of single processor computers. So examples, most PCs like that, especially the low capacity PCs like Celeron, some type of Pentium. But if you talk about the multi-core or multi-core processors machine, then that's not SIST. Okay, some of single CPU workstations and mainframes. Okay, so the process is fully sequential, not parallel. Then SIMD, actually it's this one is a recap of what we have taken in the previous section. So here you can go through a single instruction. All processing units execute the same instruction at any given clock cycle. Multi-data, each processing unit can operate on different data element. Then after that, we have this type of machine typically has an instruction dispatcher, a very high bandwidth internal network, and a very large array of very small capacity instruction units. Best suited for specialized problems, characterized by a high degree of regularity, such as image processing, synchronous lockstep, and deterministic execution. So this type of architecture is synchronous, so all processors should be synchronously working. That's why for synchronization purpose they implement something called memory locks or resource locks. Okay, and this kind of locks has a very big issue which is called deadlocks that could happen very commonly over this architecture. Two varieties here, processor array and vector pipelines. So examples of this kind of architecture is what they call it, processor arrays, like connection machine CM2, and also MASPAR MB1 and MB2. This is model names of some machines that are using this architecture. Also, under this vector pipelines, there are IBM 9000 and also Cray C90, Fujitsu VB, and Niche SX2, Hitachi S820, and some others. Okay, then we come to the MISD. Actually, the same thing, I already explained this before. That's why I'm going quickly through the slides. So a single data stream is fed into multiple processing units. Each processing unit operates on the data independently via independent instruction streams. Few actual examples of this class, because this one we say theoretical, not practical. The only model have been really built is this one. What they call it, Carnegie Mellon CMMB computer, which is 1971. Some conceivable uses might be multiple frequency filters or multi-cryptography algorithms attempting to crack a single coded message. Because this application actually could be solved by this kind of architecture, but at the same time, the MD could solve it also. That's why nobody actually manufactured this architecture anymore. Okay. Then MIMD, which is the main interest of our class, currently the most common type of parallel computers. Most modern computers fall into this category. Multiple instructions, every processor may be executing a different instruction stream. Multiple data, every processor may be working with different data stream. Execution can be synchronous or asynchronous, because each processor could work independently, and also all processors could work tightly on the same main task. That's why they sometimes require kind of synchronization. In some application, they can work asynchronously. Okay, so it can also work as deterministic or non-deterministic. Examples of this architecture in the real life is most current supercomputers, networked parallel computers like GRID, multiprocessor SMB computers, including some types of personal computers. Some general parallel terminologies here. These terminologies are very important for you guys to understand this topic. Like everything else, parallel computing has its own jargon or terminologies. Some of the more commonly used terms associated with parallel computing are listed below. Most of these will be discussed in more detail later. So what we have is task. Task actually is a kind of logical discrete section of computational work. So it's a kind of set of instructions to achieve something. So a task is typically a program or a program-like set of instructions that is executed by a processor. So the task could be a sub-program in a certain application. Okay, so maybe if let's say let us try to find a certain scenario. For example, if let's say you have an application that takes one picture as an input, then that picture has to go through under multi multi-processes to achieve multi-outputs. For example, let's say we want to take one picture by an application, then that picture supposed to be processed to get different outputs like this. I would draw something here. Suppose that this is the machine and this is a file. So this one is picture. This one is app. Then this app should produce multiple outputs. So for example is what they call it, black and white or grayscale picture. This one is 100 or maybe 90 degree rotated, and this one could be 25%, for example, zoom in, for example, zoom in. Okay, so this application should open that file, right? Then after that, if let's say the application is sequential based, then it will, at a time, it will take the data of the picture and it will run the process of making that picture as a black and white. It will convert that picture to black and white. After it finish, it's again will take the same picture, it will rotate it by 90 degrees. Then after it finish, it will take the same picture again and will do zoom in by 25%. So this is if the machine is parallel, and also if the application is if the machine is single processor, and also if the application is sequential. But if the machine supports parallel and the application also can run as a parallel, so this application should be designed to support the multi or parallel computing. So in this case, they have to have multiple tasks. So this is task 1, task 2, task 3. So task 1, T1, is going to produce the black and white. Task 2 is going to produce the rotation by 90 degrees. Task 3 could make zoom in by 25%. All of these tasks runs at the same time, concurrently. So the data, we have single data here, but multi-instructions. Single data, but multi-instructions. So in this case, this application is what they call it MISD, right? MISD, because it takes one picture, it performs a lot of tasks at the same time to produce multiple types of outputs. Okay? Is that clear, guys? So maybe this task could take like 10 minutes. This task maybe takes 2 minutes. This task maybe takes only 1 minute. So these tasks are supposed to be independent. So once this task finish, it's supposed to save the zoomed in 25% or maybe scaled down by 25% picture, and it will finish. Then that one will continue working no matter this one finishes or not, because they're supposed to work independently. So this one, it will work for 2 minutes, then after it finishes, it will save the picture. That one needs about 10 minutes. It will have to work for 10 minutes to make a black and white or grayscale picture. So in total, the application will require only 10 minutes to achieve all tasks. only 10 minutes to achieve 10 tasks, because the 3 tasks will start at the same time. This is time 0. So task 1 needs 10 minutes. 10 minutes. Task 2 finishes here in 2 minutes. Task 1 finishes here in 1 minute. So in total, we have only 10 minutes. But if sequential, if this one is sequential machine, then it will take the picture. It will need 10 minutes. After it finished, then it will take the picture again. It will need 2 minutes. Then after that, it will need 1 minute. So in total, it will consume 13 minutes. Okay? Okay. These tasks actually could be run on complete processor. So maybe if the machine is multi-processor, so maybe task 1 will be processed on processor number 1, task 2 will be processed on processor number 2, and so on. Also, if we have multi-core processor, for example, 4 cores, then task 1 could be run on core number 1, task 2 on core number 2, and so on. Okay? Anyway, what kind of architecture we have? The important thing that we have a hardware that supports really parallel processing. Then each task supposed to run in a certain or independent thread. Independent thread. Okay, so this one should be on a thread. This one should be on another thread. This one should be on different thread. And also the main application is supposed to be in different thread. That's why if this is the case, then the application could run in the parallel mode. Otherwise, if let's say we used one thread, then the entire application will work in one thread sequentially. It cannot be working as a parallel or concurrent tasks. Okay. That's why in many cases you are going to hear about something called multi-threading programming. Okay. Actually, the multi-threading programming is very advanced level of programming. So you have to create the threads, you have to know what kind of threads you have, and you always have to do thread management in the memory, and you have to keep track to your threads. If the thread finished the task, then you have to kill that thread to save your memory, and so on. A lot of things to handle in order to support or to make to produce a parallel application. So parallel application cannot be achieved or cannot be built using sequential programming. Cannot. So to produce parallel applications, you have to learn about something called multi-threading programming. Okay? Then here we have parallel task. So the task is only a single task. Parallel task means many tasks working at the same time. Okay, serial execution, exactly as I explained. If we have one processor or one core, then we have multiple tasks. So the processor will take the tasks one by one. So task 1 until it finished. Then after that, task 2 until it finished. After that, task 3 until it finished. Okay. Parallel execution means executing tasks in parallel or concurrently. Shared memory, as I explained before, distributed memory is like this. I'm not going to repeat that. Then the communication actually, parallel tasks typically need to exchange data. So maybe some parallel tasks need to exchange data among themselves. So maybe task 1 needs some data from task 2 after it achieves it. So if task 1 needs that data from task 2 and task 2 is not yet ready, then task 1 needs to wait for task 2. Then after task 1 takes the data, it can proceed like that. Okay, so this is the kind of communication. Actually, the communication between tasks is supposed to be done through the memory. Okay. Synchronization actually is very important. Synchronization is a kind of coordination of parallel tasks in real time, very often associated with communications. So synchronization without communication cannot happen. So communication is very essential to have such kind of synchronization. Often implemented by establishing a synchronization point within an application or where a task may not proceed further until another task reaches the same or logical equivalent point. Synchronization usually involves waiting but at least one task and can therefore cause a parallel. Applications will want clock execution time to increase. Sorry, this is very long. I don't like to read from slides, but I have sometimes to do because I need to explain to you. Okay, guys. Suppose that we have task 1 here and task 2 here. Suppose that also task 1 calculates A and B, and also A and B will be ready here, will be ready at this line of time. A and B is going to be ready here in the memory by this task. So here is the memory, okay? Then suppose that this task needs to read the A and B from the memory here at this time. Okay, so maybe this time is 5, this time is 0. Then here this time is 10. Okay, if let's say task 1 and task 2 starts running at the same time 0, and this one is time 10, and they are running on the same types of processors, they have the same speed, for example T1 and T2. So T2 will reach this point at time 5, which requires to read A and B, while A and B are not ready yet. So in this case, the task 2 have to do some kind of synchronization to wait until task 1 prepare A and B for it. So the synchronization actually will bring this point here. So this time actually is going to be waiting. It's going to be waiting for A and B. So that waiting actually is caused by the synchronization. Okay, so that's why synchronization could amend or could change the timing of the tasks or of the processors due to the need of some shared data that could be provided by other tasks, as we can see here. So because task 2 requires this data at time 5, and this data will not be ready at time 5, then time 5 will be shifted to time 10, or maybe 10 plus, because at time 10 exactly the A and B will be ready. So task T could perform after that. And during that time, they have nothing to do. They have only to wait. Otherwise, if they don't have synchronization, then the retrieved data from here could be wrong, maybe could be null, for example, or zeros or whatever, then the entire processing will give wrong result. Okay, so synchronization is very important to get precise and correct results out of all parallel tasks. Okay, guys? Is that clear?
Yeah, doctor.
Yeah. Here we have granularity. Granularity, I think I already explained before, right? I already explained in the last class.
Yes.
So in parallel computing, granularity is a qualitative measure of the ratio of computation to communication. We have coarse granularity and also we have fine granularity. Coarse granularity, relatively large amount of computational work are done between communication events. Back to here. This is actually a communication event. Okay, so if let's say we done a very big amount of tasks here or instructions that maybe consumes 100 seconds or 100 minutes, for example, to reach this point, then this task needs only 5 minutes to calculate something based on this. Then this is what they call it coarse. So the waiting time actually here is going to be very long between the communication event needed to perform or to complete the task 2 until it be really ready to get the needed information. So from here, based on this scenario, task 2 will wait from 5 to 100. Why? Because this system is coarse granularity. They achieve, or the tasks are divided, I mean, based on a huge amount of instructions. So what does it mean? Means every task has a lot of instructions to do. Okay, if the system is fine granularity, then each task has a few number of instructions to accomplish. Very low number of tasks or instructions to accomplish. Okay, that's why in the fine granularity, the waiting time is going to be minimized. But also, we cannot say that the fine granular is better than the coarse granular. Actually, it depends on the nature of the application. Depends on the nature of the application. Some kind of applications require the system to be coarse. Some nature of applications require the system to be fine granular. So nobody can decide until we know what kind of application we have. So as a programmer, as a system programmer or application programmer, we have to carefully understand about the nature of the application in order to be able to decide what kind of granularity to be applied, or what kind of system design we need to apply. Okay? So as we go through the class, actually I'm going to bring some examples for you. Even I will show you some programming scenarios to understand what kind of things we have to do, how we can program multi-trading programs, or how we can run them, how we can manage the trades, how we can kill the trade, how we can let a trade waiting for others, and so on. Okay, we try. If we actually, it's not a part of this course, but I would like to give you a real look to the real applications or to the real life of building parallel applications. Okay, guys?
Okay, Doctor.
Yeah. So here, observed speed up of code which has been parallelized, define it as wall clock time of serial execution over the wall clock time of parallel execution. So if let's say we have the same application, we run that application on serial machine. We run that, for example, we have application X and the same application X here, we run them on different machines. So this is serial machine and this is parallel machine. So this one is serial machine, this one is parallel machine. So if let's say when we run here the application X on the serial machine, it runs in 100 seconds, and when we run it here on the parallel machine, it runs only in 10 seconds. I wanted to use simple numbers to make it easy for you. So how much is the speed up now? Guys, how much is the speed up?
What do you mean, doctor?
Yeah, this one is very slow, right?
Yes.
100 seconds. So we want to speed up that thing, the X application, by changing the machine, right? We bring parallel machine, and we succeeded. We succeeded to run the same application on this parallel machine in 10 seconds. So the total speed up, how much?
10 times. Is it?
Are you sure? Actually, based on this slide, they said wall clock time of serial execution over wall clock time of parallel execution. That means 100 over 100. It will be equal to 10 times. 10 times faster. 10 times faster. Right? But
Yes.
also at the same time, we can calculate it in different way. So we can say 100 minus how much time we saved here. Yes, it's 10 times faster, but how much time we saved? We saved 10 minus 100 minus 10, which is 90, right? 90 seconds. Okay, okay. This 90 second. What is the percentage of the total time? It's supposed to be divided by the total execution time. Then it will be equal to 90% of time saving. 90% of time saving. Time saved. Okay, clear? Very simple, right?
Yes.
Yeah, this is going to be one of the test questions. So please, guys, be careful. And it's very simple. Is nothing. There is nothing complicated, but you have to understand. You have to understand how to calculate things. So if I said, oh, how much is the speed up, or how much time we saved in percentage, then you have to know how to calculate it. Okay?
Okay, doctor.
Yes, time is almost finished, and we have only these two slides. Let us finish them quickly to close this chapter. So parallel overhead here, the amount of time required to coordinate parallel tasks. This is what they call it, parallel overhead, and I already explained in the last class. As opposite to doing useful work, parallel overhead can include factors such as task startup time, synchronization, data communication, software overhead imposed by parallel compilers, libraries, tools, operating systems, etc., and task termination time, and so on. As I mentioned, to run a program in parallel mode, we have to have multi threads. Then the threads have to be managed, and also we have to keep a track to that threads in order to kill them once they finish their task, to save the memory, and so on. So we have to do a lot of things, including also synchronization, communication, and so on. So all of that things is considered as a parallel overhead. So if the application nature is sequential and we make it or we run it over parallel, then the time needed to execute is going to be more than the time needed on serial. Okay, because there are something called parallel overhead. So parallel overhead could be a negative, could be a negative thing that increases the execution time. This depends on the nature of the application. Also, massively parallel refers to the hardware that comprises a given parallel system having many processors. The meaning of many keeps increasing, but currently BG over L pushes this number to 6 digits. I don't know what to say. Anyway, scalability means how easy is the system, or how easy the system could be expanded, or could be the capacity or the ability of the system could be increased. So refers to parallel systems hardware and or software ability to determine to demonstrate a proportionate increase in parallel speedup with the addition of more processors. So is it easy to extend or to increase the number of processors, to increase or to expand the memory, or not? So if the thing's easy to be increased, then the scalability is high. If the scalability is low, means we cannot increase the number of processors, we cannot expand the memory. So factors that contribute to scalability include hardware, like particularly memory, CPU, bandwidth, and network communications. Also application algorithms, parallel overhead related characteristics of your specific application, and coding. Okay, that's all, guys. I hope you understand something from this class. And if you have any question, please ask me now before I close this session. Any question?
No question, Doctor.
What's about the others?
No question, Doctor.
Okay, hopefully you understand. Anyway, the video is going to be uploaded to the YouTube channel, inshallah, by today, or maximum by tomorrow, inshallah. Okay, have a nice day, and assalamu alaikum wa rahmatullah.